Remember now what we've done in this unit. We defined the notion of function at the beginning and then very quickly got into the graph of a function, and we've just spent a lot of time talking about the graphs of functions. Now we're going to switch gears and go back to the original idea of a function. And we're going to talk about something that I call the algebra of functions. We're going to treat functions as objects, and we're going to ask ourselves, can we treat them the way we treat real numbers, for example? Can we add, subtract, multiply, and divide, and possibly do some other things with them? So let's go ahead and look at this. The algebra of functions. And let me answer the question I just posed. Like real numbers, we can do what I just said. We can take the four operations. Of course, we'll have to define how to use them with functions, because when you define these operations for new objects, you have to define how they work. You know how they work for numbers, but you don't know how they work for functions until we tell you, or we define them in some way. So plus, minus, times, and division. Like real numbers, we can do all of this to functions, creating in the process, creating what you might call new functions from old. The new functions will be combinations of the old using these four operations, which we'll need to define. A second point I want to make here. There's new notation here. When we define the sum of two functions which already have names, we'll want a name that reflects the old names and the sum symbol. The same thing with difference, multiplication, and division. So there'll be new notation here. Also, the new functions we create. Put a line here. The new functions, how will their domains differ? How will they be connected to the domains of the functions of which they are made? So the new functions have domains which are those elements common, is the way I'll put it, common to the domains of their component functions. Now, this will all make more sense as we do examples. The new functions, the ones that we create from sums, differences, products, and quotients or divisions, will have domains which consist of those elements common to the domains of the component functions. Now, there will be one proviso there, except where division by 0 turns up. Now, that's a rather vague introduction to the domains of such functions, and we will specify that in a moment. But I wanted to at least set the scene for you. We're going to try and perform these operations on functions. There'll be new notation for them, and the domains will have to be accounted for. Okay. Well, let's recall something. Remember, I had some pictures that showed functions as machines. Well, remember how I did that. Here's a little picture of standard sort of function machine. And if I call the function h, remember you can think of it as h of something, h of box. And then what happened? The x's went into the function and they came out looking like h of x. So the h, or the h of box, stood for the function itself, for the machine, the correspondence. The h of x is the element that came out of that correspondence, the element which is h acting on the domain element x that went in. So you want to keep that in mind as we go, because we're going to be talking about the functions and the things that are the result of functions, the range elements, and I want to keep them separate for the notation that's coming up. So for what's coming up, let us suppose, because I need to have some letters to work with, suppose f and g are functions. Okay? And then with these functions, I will define the functions that act like the real number functions. Definition. The sum, SUM function, f plus g, that'll be the name we give this function, seems like a good name, is defined by, now here's the clue, f plus g of x. Now see, f plus g, since it's not a single letter, I need to put parentheses around it. So this is a new use of parentheses. Okay, keep that in mind. I have to put the parentheses because there's more than one thing here. But this new function, this f plus g function, acts on x. How? I will define it to be, you take f of x, which is well defined because f's a known function, and you add to it the value g of x, which is also well defined because g is a known function. Now, there is something implicit in what I just said. The x's that are allowed here are x's that have to work for f and for g simultaneously. So the only x's that are allowed are those that are common to the domains of f and g. So one would write then, perhaps, and we'll try and simplify this later and maybe look at a picture, the domain of f plus g would be all the x's in the real numbers, this is that set builder notation we've seen before, such that x is in the domain of f and simultaneously x is in the domain of g. Now there's a shorter notation for that, but we haven't talked about that, and I'd rather use the words here in this course. So what we have here, and we'll go ahead and look at some pictures now to try and get this straight, is that we've got this new kind of function that, let's see if we can draw this picture. Here we have the domain of f, and out of the domain of f comes an x. And the x goes into the f function, which I've denoted by a box here, and comes out as f of x. Okay, we've seen that before. Same thing happens with g. Here's the domain of g. Out of that comes an x value. It goes into the g function. That is my g function, and it comes out as g of x. Okay? What now will I do with this new function? How will I describe its domain? This will be the f plus g function. Now we know what comes out. F plus g of x, which has been defined to be f of x plus, that's the definition of it, f of x plus g of x. Now how are we going to describe what goes in? The little x's here. Well, where are they going to come from? They're going to come from, if I take domain f here on the left, and domain g here on the right, and I take the parts that are common to both, see? The x's that are in both, those are the x's that are allowed into f plus g. The x's that are in here, that are common to these two domains, if they happen to intersect. Now if they don't intersect, then f plus g will be an undefined function because there will be no domain for it. So it'll be the domain that can be visualized in that manner. Well, now that I've done the visualization for f plus g, I hope you see that the same idea is going to work for some of these others. For example, definition, and I'll shorten my wordage a little bit here. Likewise, okay? Likewise, the difference function, okay, the difference function, which we'll call f minus g, which seems again like the right kind of name to give it, we will define by f minus g of x, and here will be the definition. It will be f of x minus g of x. So I'm defining this funny function, this f minus g function, to be f of x minus g of x, and what x's will work here? Only those x's that are in the domain of f and the domain of g simultaneously. Similarly, one can define the product function. The product function, f times g. Now please note, I'm going to be using dots in a different way later on. This is a closed, blacked-in dot, okay? It's just a dot like that. We will define this function by f times g of x will be f of x times g of x. And again, this side, we're doing this by definition now, this side will only be defined for x's that live both in the domain of f and the domain of g. I might also point out that since we often drop the multiplication sign when we do real numbers, variables that is, like we write x times y, we'll just write xy. We can do the same thing here. We can just write fg of x. That is also done. So in all of these, the f plus g, the f minus g, and the f times g, the domain of the new function is simply the elements that are common to the domains of the functions that make it up. Now we come to the usual problem, the divisor function or the quotient function. And you know what's coming up because I've already hinted at it earlier. Here we go, the quotient function. This is a quotient, the quotient function, and we'll give it the name f over g. That seems again like the proper name for that. Is defined. We'll go back and put in some extra words here because this is a special case. F over g of x. So there's the name of the function. I am now defining what it is. It is defined to be f of x over g of x, which is pretty much what you expected. And you can see where the problem comes. G of x may be 0. And if it's 0, then f of x over g of x is undefined. So here what we need, and I'll do this in pictures, we want g of x not to be 0. Before I write that down, let me see if I can draw a nice little series of pictures here. So imagine that this is domain f and this is domain g. Now normally we would just take what's in here, what is in both of these sets at the same time. But now I want to imagine a third set cutting into this, and this is the set where g of x is equal to 0. Now that part I don't want. So I want the parts that are common to domain of f and domain of g, as I've shaded in here, but I don't want anything where g of x is 0. I have to toss that out. So adding this to the definition, this is only going to occur where g of x is not 0. So I don't take just what's common to the two. I take what's common and what doesn't make g of x 0. Okay, well with that proviso, and in practice it's really very easy to keep track of this. The function on the bottom, obviously you have to toss out a number that makes that 0. Okay, let's go ahead and look at an example or a series of examples to practice this. To do this, I will take a function f of x and let's just say the square root of x plus 1. And I'll take a g of x to be, say, 2 over x. Now, since I will be discussing these new functions and their domains, let me write down the domains of these while I'm here. Let's see, the domain of f. Well, we can probably do this with a little thought. We want x plus 1 to be greater than or equal to 0. So we want x to be greater than or equal to minus 1. I've just done a small equation in my head. So I think you can see that. So minus 1 to infinity, of course, then will be the domain. Minus 1 is what makes this 0. If I were to go below minus 1, of course, I'd have something like minus 3, and that would be a negative under its square root, which is undefined. The domain of g, similarly, is even easier. And let me really use shorthand on this. Let me say it's all the real numbers minus the set containing one number, 0. Because we have division by 0 as a problem there, and we have to eliminate it. So in pictures, if this is minus 1, we want to include minus 1 and go off to infinity to the right. So there's my picture of the domain of f. The domain of g can be pictured this way. There's a hole, it goes off to the left and right forever, but there's a hole here at 0. Now, I think all of that will help us as we look through these combinations down below. The algebra of functions, we're now going to use those 4 operations. Let's see, what would f plus g of x be here? Well, by definition, that's f of x plus g of x, which here is the square root of x plus 1 plus 2 over x. Well, that's easy. Nothing special there. F minus g is going to be f of x minus g of x. Of course, that's square root of x plus 1 minus 2 over x. Again, no problem in either one of those cases. And likewise, f g of x, that's the product, is f of x times g of x. And that's simply square root of x plus 1 times 2 over x. And again, there's no problem with that. And the domain of all of these will be the same as we saw before. And what would that be? That would be what's common to these two domains. And it's easy to see from the picture what would be common. We start at minus 1 and we go off to infinity to the right, but we have to forget about 0. That has to be dumped. So that means we actually have two intervals, -1 up to 0, not including 0, and then 0 up to infinity. So the domain in all cases, here, these three cases that is, let's see, square brackets, -1 to 0 open, or open 0 to infinity. So we've left out 0, but we've kept everything else, and so we have the common domain. Now let's look at the problem child. Let's look at f over g of x. Now by definition, that's f of x over g of x. And in this case, that is square root of x plus 1 over 2 over x. Now, there would be only a problem here if g of x could be 0. But 2 over x can never be 0. No matter what number you choose for x, 2 over x cannot be 0. No restrictions this time. This is really lucky, because in general there will be a restriction of some kind. But there are no restrictions, so the domain is the same as the ones above. So this turned out to be nice in that last case, but that won't always be the case. And what you'll do in a lot of your homework problems now, you will look at these general functions and you will put in various numbers just to see how they would calculate. For example, if f plus g of x is square root of x plus 1 plus 2 over x, if we wanted to know what f plus g of 1 is, we just put a 1 in here and a 1 in here and see what number we get. So that's something I think you should practice on your own. And in fact, we'll pause now so that you'll have a chance to do that. We've looked at now functions added, subtracted, multiplied, and divided, and looked at their domains in a couple of examples. Now I'm going to show you a new operation that you can't do with real numbers. See, this is an operation that is unique to functions. A new operation unique to functions called composition. And because you can't do it with real numbers, it kind of opens up a whole variety of possibilities. And it's exciting to look at these new objects that we call functions and see what can be done with them that can't be done with our old friends, the real numbers. So, under composition of functions, let me make the note that I just made. This is a new combination of functions that has no meaning in the real numbers, has no meaning in R. Okay, this is something that's totally new, and it is very important for the kind of work we'll be doing later. You've already seen a little bit of this and you didn't realize it. But let me go ahead and lay out the idea here. And it's a simple idea once you think about it. We have seen functions represented as machines. And here's my little machine, and we have an x value that goes in coming out of the domain of this function. The function might be called f, or f of box if I want to indicate the correct notation, and out of this function would come f of x. So we have a domain element, the actual function, the machine, the correspondence, whatever you want to call it, and the range element that comes out. Now, here's what's new. Suppose we take the range element, and instead of stopping there, we put it into another function, treating it as a domain element. So we take the f of x and put it into a new function, this function. And I'll call this g of box. Now, what would come out of that? Well, what do you think would come out? The f of x would go into the box, and you'd end up with g of f of x. This is a combination of functions unlike what we've seen before. It's not the sum, it's not the difference, the product, or the quotient. It is a new combination of functions. It is gotten by taking two of these function machines and treating them as one big machine. And that's the key here. This is what will define this new function. Let me draw it that way. What we have now, thinking of it in pictures before we get to the proper definition here, we have one massive function. So the little x domain element comes in at the left, and it comes into this new function g of f of box. So it's g acting on f, which acts on the x, which comes in. And it results in g of f of x. So all I've done is taken the two functions from the previous page, and I've hidden them. They're in this big box, which we now can label this way. So, two functions hidden within. And they form this new function, which is a combination of functions which is unlike what you can do with the real number operations. So let's go ahead and define what I mean by this. Definition. The composition is what it's called. That's the word that's being used. And we say we compose two functions together. The composition of two functions, let's call them f and g, as above, meaning as in my pictures a moment ago, is defined by, and you'll get new notation while we're at it. The new notation is this. Remember what I had a moment ago. Here is my picture. X went in, and the function was g of f of x. So g was the last thing to act. F was the first thing because f is closest to the middle. It acts on the x first, and then the g acts on the f of x. So we'll define the function, and we'll use this new notation. G open dot f of x will be, by definition, g of f of x. Now I'll talk about the domains involved here because of course, the f of x has to be something that lives in the domain of g, otherwise the right-hand sign doesn't even exist. But let's talk about this notation a bit. Notice that when you use this, you have to put it there. You cannot abbreviate it because g next to f would be multiplication. That would be the closed or the blackened in dot that I talked about before. This is an open dot, or an open hole if you like. So be careful when you write it, don't get sloppy. Keep that as an open hole because this means composition. It doesn't mean multiplication. That's a totally different function. And as I said, the domain here has to be carefully defined. So let's go ahead and write that down. The domain of g composed with f, g composed with f is the way this is often read, is, and I'll use that set builder notation, it's a set of x, but what's the first thing that happens to x here? The first thing that happens to x is that f acts upon it. So that means x has to first of all be in the domain of f. So it'll be the set of all the elements x that are in the domain of f such that f of x, which is in the range of f, which is the result of f acting on x, such that f of x lives in the domain of g, so that g can then act on it. So f of x is in the domain of g. So x is in the domain of f, and those x's such that f of x are in the domain of g are the domain of g composed with f. And I think that makes sense when you see it in the boxes in the pictures. Let me go ahead once again to show you a box picture to kind of illustrate what we have here. The big new function here in my generic machine shape here will take x's in and produce out g of f of x's, which can also be written as g composed with f of x. That last part is the formal definition, and the first part is how you would actually calculate it. And what's happening inside? Well, internally, you have two little machines doing their jobs. This is f of box, which produces a little f of x, which then goes into this other function g of box, and then the result of that goes out of the big machine. The big machine, of course, is g composed with f, but it's made up of these smaller machines on the inside, and this is what's happening inside, and that's why the domain was defined the way it is. Again, the x has to be able to go into f, so that means the x has to live in the domain of f. So it has to come out of the set domain of f. But when it comes out and becomes f of x, that f of x must go into g. Not all of the things that result from the function f will be elements that can go into the domain of g. So this thing must live in the domain of g. There'll be other things that come out of this function that won't. Those that live in the domain of g, those x's back here, will form the domain for this whole function. Okay. Now, with the pictures, we need to do some examples. Let me give you one warning note before we do any examples. And all of this, I hope, will pull together when I look at these specific examples that I have in mind. The domain of the composition of the two functions, g composed with f, okay, the domain of this, I want to warn you, cannot be determined just from the form of that g of f of x formula that pops out at the end of the function. It cannot be determined just from the form of that. The reason is that the history, if you like, that's one way to put it, the history of the composition, that is to say, the history of the composition, i.e. of f and g, the two elements that make up the function, must be considered. You cannot forget where you came from when you're looking at a composition of two functions, because these functions have restrictions on their domains to begin with. Those restrictions are carried on through and appear in this composed function. Although the formula here may not indicate that, you have to remember where it came from. Now I'm going to show you an example to illustrate just what the problem can be. So it's a little bit tricky to keep this in mind. Example. Here's a function, f of x equals square root of x, and here's another function, g of x equals 1 over x squared. Now, we're going to talk about the composition of these two functions, so let's go ahead and write down their domains right now. The domain of f, this is well known, this is going to be all the numbers from 0 to infinity, including 0. Square root cannot take the square root of negative numbers. For x, there's only one number that must be eliminated, or for g rather. So the domain of g is going to be the real numbers minus the set containing 0, as I indicated before. All right. Then let's go ahead and examine g composed with f of x. Now, as I'm doing this, we'll have a chance to work with the notation and get a feel for it. G composed with f of x is, by definition, this is a definition equality, is g of f of x. Now that's something that's easy to calculate because f of x is given to us right here. Everyone can do this first step. So this is g of the square root of x. No problem there. Now the next step requires a bit of thought. You are applying the function g to the object square root of x. So you want to think of this function, that's why I left a little space here. You want to think of this, as we've done often before, as g of box equals 1 over box squared. And now it really comes into play and becomes very important for your understanding. G of box. The box happens to be filled with the square root of x. So g of square root of x is equal to 1 over square root of x squared. All right, so it's 1 over whatever was in the box, square root of x squared. Of course, square root of x squared is just x. So this then is the form of the composed function. Now, let me make my point about the domains. The domain of g composed with f is equal to 0 to infinity, not including 0. Why is that? Well, the square root function, which is where this original x comes from, only allows a 0 to infinity including 0. But when we get to the g function, its domain eliminates 0 as a possibility, so we toss out the 0 and we're left with 0 to infinity. This domain equals that due to its history, not the real numbers minus 0, which is what this 1 over x form would suggest the domain is, due to its form. So you have history versus form here. So if you're given a function like 1 over x, and you're not told anything about where it occurs, where it comes from, then you are right in assuming its domain is the maximum domain allowable, r minus 0. However, if you are told that this is the result of the composition of these two functions, for example, then you must take into account their domains, and that restricts the final domain of this. So this is the function 1 over x restricted to 0 to infinity. It is not the general 1 over x function, which has much less restriction. It is only restricted to not be 0. So this is a point I wanted you to keep in mind. It can trip you up if you're not a little bit careful. Well, while we're on to this new operation, let's see if we can discuss some other things. Here's another warning. Remember, when you add numbers or you add functions or multiply, you can do it in either order. It makes no difference. That's a property called commutativity. However, when you divide, the commutativity doesn't work anymore. Same thing happens for composition of functions. In general, there will be special cases where this holds, and they'll be very important to us later. But right now, in general, g composed with f is not the same thing as f composed with g. If you take two arbitrary functions, they will not compose in the opposite orders and be the same function. To show you what I mean by that, let me show you a counterexample. A counterexample to the hypothesis that they are always equal. I just have to give you a couple of functions here. Let's take something easy like f of x is x plus 1, and g of x is equal to 1 over x again. And since I will be doing some calculations with them later, I'm going to remind myself that means f of box is box plus 1, and that means g of box is 1 over box. And now I just have to check that g composed with f and f composed with g are not the same thing. Well, g composed with f of x by definition is g of f of x. G of, well, f of x is right there. That's x plus 1. Then looking at this box, I realize g of box is 1 over box, so g of x plus 1 is 1 over x plus 1, period. While f composed with g of x, which is f of g of x, which is f of, well, there's g of x, 1 over x, put that in here. And then I look to f in the box form to remember what it does. It's f of box is box plus 1. So f of 1 over x is 1 over x plus 1. And these two functions are not the same. If you have any doubts, put in a simple number like 1. If you put in 1 for this function, you get 1 over 2. That's a half. You put in 1 for this one, you get 1 over 1 plus 1. That's 2. So these functions are certainly not the same, which is an example that shows that g composed with f and f composed with g are in general not the same. When they are the same, we say that the two functions are inverses of one another. And that is a topic we'll take up later on in this course. Let's go ahead then and look at a pair of functions that will allow us to illustrate some of what we've just done and practice a little bit more with this notation. Let's take f of x equals 3x plus 1, just to be different, and take g of x to be x squared. And again, when I'm doing these compositions, just to make sure I'm not going to confuse myself, I'll rewrite this as f of box is 3 times box plus 1, and g of box equals box squared. That way, whatever goes into the box, even if it's not just an x, I will know what's supposed to go on. Then, we can say a bunch of things here. If we look at f composed with itself, we never said composition had to be two different functions, did we? We can compose f with itself. That would be f of x. That would be f of, well, f of x is right there, 3x plus 1. And then, remembering the box form, 3x plus 1 in the place of the box, I'll get 3 times that plus 1. So this is 3 times 3x plus 1 plus 1. And that's f composed with itself. And just to simplify that, that's 9x plus 4. Then f composed with g is, running through this, f of g of x. That's f of x squared, just copying down g of x. That's the easy part. Then f of box is 3 times box plus 1. So this is 3x squared plus 1. So my first f composed with f is 9x plus 4. My f composed with g is 3x squared plus 1. Here's g composed with f. Now you should suspect that these are not going to be the same, because in general they're not. G of f of x, that's g of f of x is 3x plus 1. G of box is box squared. So it takes whatever's in there and squares it. So this is 3x plus 1 quantity squared. And again, that's different from all the others going before. And then finally we have g composed with g of x. And that's going to be g of x. Now this one you should be able to figure out just by thinking about it. G of x is the square function. And what does g do to something? Well, as I just said, it squares it. So if you square the square, you get x squared squared, and that's x to the 4th. So there is a 4th function that's different from all the others. And in every one of these, you'll notice this column to this column is where the thinking went in. Okay? The rest of it, the notation takes you along. To go from this first column to the second is just the definition. To go from the second to the third is fill in the blanks, F, G, F, G. But to go from the third to the 4th, you have to understand what you're doing. You have to understand that what the function f does and what the function g does. That's why I have people write these out with boxes. That helps you understand what the function's all about. It doesn't confuse you with a particular letter like x. And I think that's very helpful, so I hope you'll adopt that process. We're going to talk about decomposing functions. Sounds sort of awful, doesn't it? Sounds a little bit like a compost heap in the back of your yard. But it's not. What we're talking about is taking a function that has been composed from other functions and breaking it back down into pieces. This turns out to be very helpful, for instance, in calculus. Let me do this simply by doing an example. Here's what I want to do in this example. I want to write h of x, which is the square root of x squared plus 1 in quantity, as a composition of functions. And I'm specifically not going to say how many functions. Well, at the minimum, we want it to be a composition of 2 functions. Now, it's not very hard to see how this might work. You simply have to imagine how this might have been constructed, starting with x and moving up to this in 2 steps. One way to do it is, here is one solution, I'll put 1 here. I might let f of x be the function x squared plus 1, and let g of x be the function square root of x. Now again, to remember what these do, rewrite g of x as g of box is square root of box. Now you should see how this would work, because then you can think of h of x as being g of f of x. Because if you finish this off, g of f of x is g of x squared plus 1. And then what does g do to something? G of box is square root of box. So this is square root of x squared plus 1. So there's one way to decompose this function into 2 other functions. And the point of doing this, of course, is that the 2 functions that make this up are simpler than the original function. And therefore, you could do some operations on these that might be hard with this original function. Let me show you one other way to do this. You can break this down even further. You can say, I'm redefining my f's and g's now. F of x maybe is equal to x squared, say. G of x would be the function that adds 1, so x plus 1, and then make, say, k of x, because I need another letter. K of x would be the square root of x. Then you could say that h of x is equal to k of g of f of x. So we've made it a triple. That's k of g of f of x is x squared. That's k of g of x squared, g of box is box plus 1. I didn't write the boxes this time, but that's what it means. So this is x squared plus 1. And then finally, what's k of something? K of x is square root of x, so k of box is square root of box. The x squared plus 1 is in the box, so this is square root of x squared plus 1. And lo and behold, we're back to h. This was 3 steps, this was 2 steps. All that this is for is to show you that functions can be decomposed. And so on that note, I will stop on composition of functions. And finally, at the end of this unit, we will talk about what you might call word problems, but we're going to call creating mathematical models.